Hi, it's Terry Dennery of the MathWorks. So this video is going to be called something along the lines of fidelity, speed, and the grade system model. Okay, and so as I go through this, I want to begin to define what the grade system model is, but certainly it's great, and it's great according to really what it does for you. Okay, and so let's talk about the fidelity piece. The fidelity piece is, well, how much do I need to put into this so that I really have something that's useful? Well, the answer, unfortunately, is it depends. It depends on what you're really trying to understand. And in a way, what it means, and I think this is ultimately a really good thing, is I can't tell you. It's really, the projects that you work on, the things that you're designing, they're going to be a little bit different, and what you're going to need to understand is going to be a little bit different. Okay, but in my opinion, that's what makes it so much fun. Okay, and so anyways, I would make the case that this is a very high fidelity model. We can see it represents the mechanics, all right, and the motion that we want, as we kind of um, analyze what we're designing, we're seeing it's doing really, really well. That we're, asking for a angle transition of a full rotation or 2 pi to occur in like 1/2 second, and this top curve seems to indicate that it's doing it quite well. Now, if you take the first derivative, which is really kind of observed speed, you'll begin to see a little bit of difference between what we're asking for and what we're getting. I can kind of zoom in here. You'll kind of see, a little bit of more departure there. Okay, but for the most part, I'm pretty happy with it. And why does it work so well? Well, it's because it's delivering the torque that's required to make this thing move the way I want it to, right? And so in this example, we also are really understanding it electrically. That torque is ultimately generated by an electric motor, and it's able to kind of deliver what's needed according to the voltages and currents that we're seeing here. All right. So along the lines of, what's my very useful um, system model? Well, I'm going to give you an example. The example is that I want to switch from this idealization of the mechanics you see here to one that's provided by CAD. And I'll even show kind of the work I did, very simple work in MATLAB, where I assessed, let's see, right here, the difference in mass, right? So as I added kind of those more bulky connections, I add a little bit of mass to the linkage, and we'll see that it's overall about 4.2% heavier. Okay, so seems like that should make a difference, but the thing I want to get into is it actually does present kind of an interesting design problem from a controls point of view, because the qualification of software can be very expensive. We have lots of customers. It's millions of dollars that they spend to make simple changes, or at least what we would perceive as simple changes in software. It's never simple, of course. But what I wanted to get at is this idea that we kind of presented in one of the earlier demos is kind of the specifics of the control algorithm, a piece of it being feed forward and a piece of it being feedback, and the PID is a feedback. But the feed forward is, essentially understanding your mechanics really well and representing it properly in your feed forward component. Well, if I'm going to switch to the CAD version and it's 4.2% heavier, I know that this feed forward piece is not going to be perfectly representing that anymore, right? And I want to understand how big of a problem that is, right? And so I'm going to bring up this tool I like quite a bit that's part of Simulink. It's called the Simulink Data Inspector, right? And so essentially, as I showed earlier, that if you know your equipment real well, the feed forward piece should do most of the work, right? And what we're looking at in red is the feed forward contribution to the commanded torque, and then the blue is the contribution coming from feedback, right? And so in simulation, that feedback was almost zero compared to the feed forward, but here we're seeing it's a little bit bigger. And I studied that a little bit this morning. At first I was bothered, but then I kind of thought about, well, we're operating our control at 1,000 hertz, and for those really, really steep gradients, I'd say you can make the case that a update rate of 0.001 seconds is not nearly enough to really capture that transition without it kind of having this, kind of jagged staircase kind of look to it. And so without too much further analysis, I'm going to say, that that's the issue. Okay. But what I'm finding is that this is the figure I want to look at, you know, when I assess the quality of my feed forward control. And can I just stick with what I was using is kind of the question I want to answer. So anyways, so with that, hopefully I'm justifying what I'm about to do. All right, and so what I want to do is go back to my grade system model. I am going to reveal that this simulation took me 8 minutes, and if you really care about voltages and currents in the AC motor, you might say that's a bargain still. But for me, I'd like it to be way faster than that, right? And so what I want to do is just kind of validate the idea that, well, if AC motors are so great and that they deliver precisely the torque I'm asking for, in a way I don't need to model them, okay? And the advantage, of course, is that so much. So we'll go from this very detailed AC motor model, all right, to something much simpler. And we can do that because of these subsystem references. So again, getting to block parameters is off screen. I apologize for that, but once I have it, this is where I make the change. And so I am going to go from a PMSM drive to the one I call deliver the torque command. Okay. And you'll see that that's just, as it says, delivering precisely the torque that I commanded, right? And another, probably a little bit more difficult to explain, but certainly it allows, I'll say it this way, that to capture the dynamics of the currents and voltages of an AC motor, you need to operate a pretty small time step for your integration. Well, we're not constrained so tightly anymore, and so we're going to increase it by a factor of 100. And with that, and you'll see it right here when we hit run, that the whole thing will calculate much faster. So I'm just running it from the animation window. That means I'm hitting the green button in the corner. And I wouldn't argue quite yet that it's running in real time, but boy, that's way shorter than 8 minutes too. All right. And so now I want to bring up this new run, all right? And I want to compare it with this. And I had trouble in practice, so hopefully I don't this time. But let me just change the colors. And so I'm going to make feed forward yellow. Let's set that. And let's make feed back pink. Set. All right. And so let's add these. And I'll make the case that I don't really need to model the AC motor. I'm really expressing this at the level I need to study it for understanding the contribution of feed forward and feedback quite effectively. So anyways, let's go ahead and move into this now, and let's make the decision. All right. Okay. Oh, actually, it is here where we want to be. All right. And so first of all, we're going to switch to the CAD version of this. And so again, it's a subsystem reference. Try that again. Block parameters. And I'll go to mechanics 4-bar CAD. Okay, and so again, we'll view it. We'll even hit the run button here. And so you should see a change very quick. And one of the changes will be that middle bar will be yellow even, but I think you'll recognize that this will be a different model based on the CAD as defined inside SolidWorks. All right, so it looks pretty good, doesn't it? And so now I want to just check a few things, right? And I think you certainly can see it's not quite as good, and it shows up a little bit more in speed. You'll see this little bump here, I think is a little bit bigger than what we saw before. And if I come in here, you're definitely seeing the difference. And so the blue curve representing feedback now is much bigger. And the feed forward, of course, it's feed forward and it's not informed by the change at all. And so therefore it's going to be pretty much the same. All right. So the real interesting piece here will be really kind of comparing the feedback. All right. And that we are seeing a difference. And the blue is our new one, which is saying I'm mismatching my prediction of motion based on mechanics um, with what we are truly using, and I think it's kind of clear that the blue is bigger error than the pink. But again, that's kind of the point too, is that you measure it and you observe it and you have knowledge before you even make the commitment to the design decisions that are going to be hard to change. Okay, so um, anyways, again, it's a debatable point, but we have the ability to really kind of examine and look at it from various aspects. So I would say, well, if it cost me $1 million to change that controller, and and everybody's happy with this, I'd say don't do it. Okay, it cost me $10. I'd say go ahead and make the change. So. Um, So, anyways, I think just to wrap up, I am going to do one more thing. All right. And let me run this one more time just so you can kind of see this. And it's might be that I'm throwing something in at the end that's a little bit more of showing off. But I think that, again, kind of with regard to speed and fidelity being the primary conversation here, I do want to address real time being an issue here. And that even if we're happy with that, um, is it really worth the price of the animation to run that slow? And so here's where we might make the switch back to lock parameters, subsystem reference, and I'm going to go to mechanics, 4-bar, CAD, MG. And we'll click on OK. And we won't have the benefit of the animation. Okay, it hasn't started running yet. It's still compiling. I'm seeing that in that green line right there. And I'd say I feel pretty good about real time now. Okay, so anyways, very interesting topic. What's the grade system model? Well, it's going to be very personal to the project that you're working on and what you're going to need to do with it. And I'll ultimately say that whatever the grade system model is, the ability to kind of change and adjust your fidelity to get speed improvements, or adjust your speed to get fidelity improvements, that will be an important piece of it. So anyways, thank you.